another alternate for detection of single sideband modulated signals, and that is a product detector. So the distortion that we have discussed before, it can be avoided by using the product detector instead of an envelope detector. So if you're employing you're using a diode followed by a RC low pass filter for envelope detection, then you have the problem of the insertion of the carrier with correct phase and frequency. So the problem that we discussed before was, you see, if you have a double sideband suppressed carrier signal, if you're going to add the carrier with the wrong phase, okay, your envelope is no longer reflects the original audio signal, okay. So it's something like whatever it is, it's different from what we transmitted. Okay, so what we desire is like this, but then if the phase of the carrier is not correct, the envelope gets distorted. Okay, so we don't need this envelope. And even if for example the phase, this is your carrier, and if the phase is uh, uh, is different by 90 degrees, then the frequency that you recover, for example over here, is twice the frequency of the audio tone that was originally sent. Okay, so the frequency is twice, as we have mentioned before. So we don't have these problems, for example, in if you want to demodulate a single sideband AM using carrier insertion. We don't have these problems in the product detector. Okay, so the methodology is that, as the name implies, product, it's simply a mixer, so it is also known as aka the mixer. In the receiver shown in the figure below, the product detector is just the familiar multiplier. So what it does is, if you are having a super heterodyne receiver and you are receiving, let's say, the RF, which could lie in a range of AM broadcast range from 550 to 1700 kilohertz. If this antenna is receiving AM signals, then this is mixed with the local oscillator signal. Okay, and if you recall, local oscillator signal is your FRF plus IF. So the difference that it produces is the intermediate frequency. Okay, so this is plus FIF. We're not interested in the high frequencies. So the difference of these two frequencies is IF. So we have an IF amplifier over here. So of course we are having the frequency that is an intermediate frequency. So whatever in super heterodyne receiver, whichever frequency component is received, or a spectrum of the frequency received, it is translated down to the intermediate frequency. All right. Therefore, what you do is, in a product detector, is you employ a beat frequency oscillator that is going to produce the beats that's going to produce a tone at IF frequency. Okay, at IF frequency, and therefore you're going to shift the spectrum. You're going to shift the spectrum down to the baseband. Okay, so this is FIF, right, and you have FIF over here as well. So the difference of these two frequencies is 0. That is, we are going to shift the audio down to its baseband. And then there is a RC low pass filter. Okay, this is a simple RC low pass filter. Note that there is no diode, so you are not using a conventional envelope detection. So you have a mixer over here that's new. Okay, and the frequency of this beat frequency oscillator is set to IF. So the detection is going to be done at the baseband. Okay, so basically your spectrum, if let's say this is for example, if this is an upper sideband and that was translated down to FIF after super heterodyne receiver conversion, then this gets translated down to the baseband. Okay, after the multiplication or mixing, so it comes down to 0, and that's the original baseband signal, the audio spectrum. And then this can be recovered from a low pass filter. Okay, this can be easily recovered from a low pass filter, and you're good to go, right? You can hear a high fidelity sound. So the output of this detector is by distributive law of multiplication. The output is the product. Product of what? Product of the intermediate frequency components. Okay, there can be more than one intermediate frequency components. Product of intermediate frequency component times it's the intermediate frequency component times the beat frequency oscillator. Okay, so it's like the sum of the products of each IF signal component times the BFO signal. Hence it is called the mixer. Okay, so this is what the mixer does. Mixer produces new frequencies. Okay, and if the intermediate frequency stage has more than one component, then the output is the sum of the products of each. So there is sum of the products, and those products are IF signal components multiplied by the BFO signals, the beat frequency oscillator signals. So it is the sum of all those products, right? So sum of the products of each IF signal component times the BFO signal. So that's the output of the multiplier, right? And that's what the product detector is. So if you assume that there is no cross products, okay, but if the in super heterodyne receiver before, if you have the no undistorted, no distortion due to the intermodulation or beating of IF frequency components together, if there are no cross products of IF signal components, the product detectors are also called baseband mixers. So baseband mixers or baseband detectors. Why? Because they are going to shift the spectrum at the intermediate frequency down to DC. Okay, so they translate the sideband component all the way down to the original frequency. So the detection is basically being done at the baseband level or at the DC. Okay. So while a product detector does not produce across products intermodulation distortion at the IF signal components, the injected carrier should ideally have the correct phase. Okay, so if there is no intermodulation or beating of different frequency components in the IF stage together, then of course you have the correct carrier phase. Okay, so we don't have this problem. The wrong phase is of no consequence in our single tone example, right? But when the signal has many components, then the relative phase are important. Okay, so if, for example, if that can be explained, you see, if you have a system, digital or an analog. Well, analog system don't have a linear phase. So what I'm going to draw over here is, for example, you have a system like this, which has a phase response. Let's call this phi of omega. This is my phase response. Not the magnitude response, but the phase response of the system is such that it's linear. It's linear with frequency omega. Okay. If you recall, in digital systems having finite impulse response (FIR), if you have heard that term, systems which have a finite impulse response and they have symmetric coefficients, symmetric or antisymmetric, they exhibit linear phase response. So that is, if you take the gradient, okay, if you take a gradient of this line, then a quantity, so if you have a gradient like this, right, the quantity and associated quantity known as tau g of omega, which is the negative gradient, is defined as a negative gradient as minus d phi by d omega is constant. Okay, what does this mean? This means that the frequency components that start together, they arrive together. That means they suffer no distortion. The time delay of each frequency component is constant with respect to the frequency. Okay, so this quantity is known as the group delay. If the group delay is constant, you see that this is a straight line, right? And if this is a constant, the gradient is constant, then that means each frequency component, if is given a phase shift in proportionality to its frequency. Okay, so let's call this F1, F2. Okay, dot 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 to Fn. So these are a group of frequencies. Now if they start together and if they don't arrive together, then we have the phase distortion. This is not desirable, right? Well, for speech and music, it's not a big problem because human ear is not very intelligent in perceiving the phase differences. But still, to avoid um, a phase distortion in a signal, it's desirable to have a linear phase system. So what linear phase system does is they give the group delay is constant. So the group of frequencies they arrive together with the same time delay if you have a constant group delay. Okay, so what it says is a waveform will become distorted if all its spectral components are given an identical phase shift. If the phase shift for all the frequencies is the same, regardless of the spectral component and that frequency, regardless the frequency of that spectral component, well then there is a distortion. So it is only when every component is given a phase shift proportional to its frequency that a waveform is not distorted, only delayed by time. So that's all right. Okay. So if you're going to get a signal that is just xt and you're going to pass it through a certain linear phase system, having a linear phase response, and it just gets delayed by, let's say, all the frequency components are getting delayed by the same time difference, let's say capital T, then no problem. Okay, you have the shape of the signal remains intact. It's just delayed in time. Okay, so if the phase shift is proportional to the frequency, over here, the waveform is not distorted. So if for each spectral component the phase shift over here is proportional to the frequency, you don't have a problem. Okay, it has to be proportional to the frequency. The phase shift has to be proportional to the frequency so that they have a constant group delay. Okay, and they don't suffer any phase distortion. So therefore, a single sideband transmitter like the double sideband transmitter should really transmit a pilot carrier, and the receiver should lock its beat frequency oscillator phase to this pilot. Okay, so to save the power requirements for AM transmission, a small carrier can be transmitted to the receiver just to lock. So at the receiver, you can lock to its phase. Okay, so if a beat frequency oscillator locks to the correct phase of the carrier, well, then we don't have any distortion, phase distortion. Okay, so some SSB systems, they just do that, right? They send the small carrier just for the receiver at the receiver end to lock the BFO, the frequency oscillator, to the correct phase. Okay, so the BFO is locked to the correct phase as well. So if it is locked to the correct phase, you don't have any phase distortion. Okay, and this phasing is done in proportional to the frequency of each spectral component. So, but for voice communications, it is common to use no pilot. Why? Because speech remains still intelligible and almost natural sounding, even when the BFO phase is wrong. So even if the phase is off by some radians, by some degrees, it's not a big problem because human ear still does not differentiate in the phase distorted output from the original audio. So it's still alright. But if the frequency, so okay, the BFO can even be slightly off the frequency. But if you're going to change the frequency much, then of course you will hear a difference in the pitch, and it won't be the natural or the original sound that was transmitted. So a higher shift in the frequency is going to change the pitch at the output of the speaker. Okay. So if the BFO phase happens to be correct, the output will have the maximum amplitude. Okay. For our intermediate phase error, the amplitude will be reduced somewhat. Right. So we need a small pilot carrier. Okay, at the receiver with correct phase information, so that the BFO phase BFO can lock to this the phase of the pilot, and it can produce zero phase distorted maximum amplitude signal at the speaker output. Okay. So again, this product detector doesn't imply it's different from the envelope detector. You don't have a diode over here. Okay, so you're not detecting the envelopes. Okay, it's the mixer over here. So the product detector output is again the multiplication. Okay, or it's the product of the intermediate frequency times the beat frequency oscillator frequency. That is again set at the intermediate frequency. So basically you are translating the signal down to the baseband, and at baseband you have this RC filter that is going to just select this baseband signal, and you're going to listen to the original audio. Okay, even if the phase is a little offset, it's still intelligible what you're going to listen. But for correct amplitude and to avoid any phase distortion, it's convenient to have a small a pilot signal that can be transmitted from transmitter, and this information can be given at the receiver. So BFO locks to the correct phase. Okay, that is important. If it locks to the correct phase, the amplitude of the original audio is the same at the output. Okay, so before we see how we can generate single sideband modulation, well, why do we need to generate? What are the advantages that SSB offers is over conventional AM? Is that if you see that single sideband, if you are transmitting a suppressed carrier, okay, so let's say this is a suppressed carrier, and then there is an upper sideband, there's a lower sideband. So the thing is, if you select one of the sideband, let's say upper sideband, you're going to save some bandwidth. Okay, that is evident. So you don't need twice the bandwidth. You don't need twice the bandwidth. You select one sideband. That also means that the noise that is there in the entire spectrum or the band of frequencies is reduced by half. So there's a 3 dB improvement in SNR as well. Okay, so you have only this much of noise. So that's the other advantage. So you're going to, first of all, you're going to save power by suppressing the carrier. Then selecting one sideband means that you save the bandwidth, so you can have twice as many channels, okay, on the same AM broadcast channel. And plus you increase the SNR. So the sideband, besides not wasting power on a carrier, uses only the half the bandwidth. So the given band can hold twice as many channels, right? So the given AM band, for example, can hold, yes, of course, if you are going to reduce the bandwidth by half, you can hold twice as many as channels. So halving the receiver bandwidth also halves the background noise. So there is a 3 dB improvement, okay, because this noise is halved. So there is a 3 dB improvement over the conventional AM signal to noise ratio. Okay, right. So when a spectrum is crowded by the conventional AM signals, their carriers, they produce annoying beats. They are beat nodes in a receiver. So carrier anywhere within the receiver passband appears to be a sideband belonging to the spectrum of the desired signal. But in a single sideband suppressed carrier schemes, you don't have the carriers, right? So there are no beats. So with single sideband transmitters, there are no carriers, and since there are no beats, so radio amateurs, military aircraft flying over oceans, they use single sideband. Okay, they use the single sideband for radio communication over short waves for the frequency of 1.8 to 30 megahertz for voice communications for these reasons, right? So how do we generate the SSB? Since we know that there are advantages of SSB over conventional AM, so at least three methods that we have that we introduced before, but I think we talked about the first method that required a band pass filter. So you see what happens here is you have a tonal signal, okay, that is just a single tone, okay. So this consists of single tone at omega A, okay, and this spectrum is symmetric, omega A minus omega A, that is my spectrum of the tone that I wish to transmit. And then once it gets mixed up um, with the carrier, then what happens over here is that here you can see that you have two tones, right? One at omega A plus omega C, then you have the difference omega A minus omega C. So at the center omega C, the spectrum simply shifts from 0 to omega C, okay? So it's going to shift from 0 to omega C here. So you have this component is omega C minus omega A. Note that cosine is an even function, so it doesn't matter if it's minus omega A, omega C minus omega A or omega A minus omega C, it's the same thing. So then you have omega A plus omega C, right? And basically this thing is again what you have at, for example, if you're considering this, you continue plot this is 0, and down the line you have this thing repeats at minus omega C as well, okay? Again you have these two components like this. So that's your modulation, okay? So that's your modulation with a suppressed carrier. Then if you use a band pass filter, which could be a very expensive piece of a crystal oscillator, or it could be a mechanical resonator with many sections depending on the voice data spectrum requirements. And if you're going to pass the upper sideband, well, you can, for example, if you're going to select this, and you're left with this term, cosine omega A plus omega C. Therefore, you select the upper sideband. Okay, so that's band pass filtering. That's band pass filtering, selecting the frequency of the part of the spectrum that is desired. So you can still generate a single sideband. This is a single sideband. Okay, single sideband generated from a conventional double sideband, but you're using a band pass filter, so you can select either the lower sideband or the upper sideband. For example, over here, consider an input audio spectrum that consists of certain range of frequencies. Again, the spectrum is shifted, so 0 is shifted to a certain frequency, that is the carrier omega C. Ideally, you should have this spectrum, the shape of the spectrum should have remained intact. But you see over the voice channel, if this is the voice communication data, the filter shape is like this. If this is your filter shape, then this is what you get. Okay, the single sideband spectrum obtained with the filter. So you will have some loss in data at the low frequencies for the voice channel. So well, that's what the filter shape. You can't have an ideal filter. Okay, you can't have an ideal filter with a very sharp cutoff like this. Okay, such filters are ideal because they are not realizable. Okay, you can't realize them. It requires infinitely large sections, and also they are non-causal, so they don't exist. Okay, what you can have is something like this. Okay, it won't have sharp skirts, but some roll-offs like this. This is more practical. So this is a problem in well, you have a practical bandpass filter, so there will be some loss. So 3 well-known methods to generate single sideband. This is the first one and the easiest one. So in the filter method shown in the figure below, a sharp bandpass filter removes the unwanted sideband. So for example, if you're going to select the upper sideband, the lower sideband is gone. So this filter uses the crystal or other Q mechanical resonators and has many sections. Okay, so depending on the sharpness or the selectivity of the filter, you might require many sections. So it's never tunable. So the SSB signal is generated at a single frequency, which could be a transmitter intermediate frequency, and then it's mixed up or down to the desired frequency. The filter, in as much as it does not have an infinitely steep skirts, will cut off some of the low frequency end of the voice channel. Okay, so it doesn't have very steep skirts, and we have some cutoff at the voice at the lower frequency of the voice channel. So we have this cutoff over here, right? So this is bandpass filtering method of generating an SSB. The other is if you the second method is the phasing method. So it requires two multipliers. Okay, so if you have a single let's say you have a single carrier, cosine omega ct, and if you look at this trigonometric identity, then plus minus will yield minus plus omega c, omega a. You can select the upper or lower sideband by, so if you, this means you need an adder, okay, this means you need an adder, and this adder can be converted to subtractor by inverting one of its input, right? So you need an adder, it can be an op-amp circuit. Then you need two mixers over here, okay, so this implies you need two mixers. There will be two mixers, one here, the other for the second term, okay. So you need one adder, two mixers, and you see that in the second term you require sine omega ct as well. So you require, and then for the audio as well, so you require two phase shifters, two multipliers, one adder. So the phasing method again uses two multipliers, two phase shifters to implement the trigonometric identity, which is given as follows. Now, if you realize this trigonometric identity, you can still generate an upper or lower sideband. And here the subscript A, over here they denote A is for audio and C denotes for the carrier. So A is for audio and suppressed carrier frequencies. If the audio signal is cosine omega t, we have to generate sine omega t needed for the second term, and that requires the phase shifter. And 90-degree audio phase shift can be built with the passive components, or if you are having this whole transmitter on a single chip, you can use digital signal processing techniques to generate phase shift. So let's have a look. You see over here you have two mixers. There are two mixers over here, okay, and they are going to generate these two terms, sine omega ct, sine omega at, okay. So that's what it is. And if you're going to add them up, if you're going to simply add them up, you're going to produce a lower sideband. This is my lower sideband, okay. So two mixers, one adder. Sorry, this is lower side. So there's one adder, there's two mixers and two phase shifters. Okay, so if we start with an audio input, and this goes through the phase shift, this produces sine omega t, and then we have another input, that is the carrier over here. This goes through also a phase shift. So this the upper mixer produces the second term with sines, not cosines. Okay. For example, the audio signal is also phase shifted by 90 degrees, so this is a sine term. The cosine is also phase shifted by 90 degrees, so this is another sine term. So you have the second term is realized as such. So for the first term, they're simply mixed without any phase shift. So you have cosine terms, cosine omega c, cosine omega a, and you add them up. You realize this trigonometric identity to yield a lower sideband. Okay, lower sideband with negative. Okay, because you're adding them up. This is the negative. So the audio phase shift network is usually implemented with two networks, one ahead of each mixer. Their phase difference is close to 90 degrees throughout the audio band. The second term also requires that we supply sine omega ct. So you see sine omega ct in the second term over here. But since omega c is fixed, anything that provides a 90-degree phase shift at this frequency will be sufficient. So in this figure, if the adder is changed to subtractor, so if we have a subtractor over here, then that means we are going to have a upper sideband. Okay. So by inverting the polarity of one input, the output will be the upper than the lower sideband. So you select the polarity. You can change the polarity of the input. Okay. And it's still going to add up, and you can select either the lower sideband or the upper sideband. This method still generates single sideband modulated signal. Then we have a third method which is famous and goes by the name of Weaver's method. It requires four mixers, four multipliers, two low pass filters. Okay, so there are two low pass filters and four mixers, and then it basically generates over here is the lower sideband. So this third method, the advantage is it neither requires sharp band pass filters nor it requires phase shifters. Okay, so Weaver's method is shown in the figure below over here, and uses four multipliers, two low pass filters. The trick is to mix the audio signal with the first oscillator whose frequency is omega naught, and is in the center of the audio band. Okay, the output of the first set of mixer have a 90-degree phase difference. Okay, so this output of the first mixer, it naturally has the desired 90-degree phase difference. The second set of mixer works the same way as we saw in the phasing method. Okay, so the second set of mixer, they actually produce the output, and then this is added to produce the lower sideband, which is the same part as we have seen in the phasing method. So analytically, these equations are given in your chapter 8 of Hagen. So if you see at this node V1 is the low pass operation on sine omega AT and sine omega naught t. That's your output of the mixer, and this goes to the low pass filter, and that's your V1 over here. Okay, so V1 is going to select the uh, the frequency component that is in the passband of the low pass. So the lower frequency component is the lower sideband, omega A minus omega naught, right? Then well, you expand this trigonometric identity just like before over here. Uh, so you have two. Anyways, you have two signs, and if you're going to expand them, they will be cosine terms, okay, having sum and differences. So the only difference, the lower part is selected from the low pass filter. Okay, then for the second signal V2, which is at the output before the lower mixer, this is your lower mixer. So this is going to low pass sine omega AT. This is sine omega AT multiplied by cosine omega naught t. Over here, this signal is going to low pass filter to produce V2. So we have sine omega AT from the audio. Okay, then we have cosine omega naught t. So the lower is again the omega, the difference frequency, omega A minus omega naught. We are not going to select omega A plus omega naught. If you're going to expand this identity, you have this omega A plus omega naught. There is another term that's coming up, but you're not going to select that, the low pass filter. So the low frequency is selected in these two equations. Then V3 is again a mixer output. So you mix it up. You mix V1 with with cosine omega c minus omega naught. So over here you can see that you have this term cosine omega c minus omega naught, and this term comes here, right? So this is here cosine omega a minus omega naught with a half. Okay, and if you're going to expand these two cosine functions in a trigonometric identity, well then there is a there will be a high frequency term 2 omega naught t, okay, with a difference frequency. Similarly, if you are going to multiply sine omega c minus omega naught for the lower mixer over here, sine omega c minus omega naught multiplied by omega a minus omega naught over here, then again you have a high frequency output at 2 omega naught, but the sign is, look at the sign, these are two sine functions, right? So this is plus, this is minus, and if you're going to add V3 and V4 over here, you're going to add V3 and V4 over here, the high frequency components, they simply cancel out, right? So this thing is gone, and what you're left with is half cosine omega c minus omega a, which is in fact a lower sideband, right? So this method still generates a lower sideband signal and saves the bandwidth requirement and improves the SNR by 3 dBs. So we see that from equation 8.6 that this particular arrangement generates the lower sideband, right? These are three methods for generation of single sideband AM.